Hello everyone, I would like to welcome Volker Krause, who is going to talk about domain-specific debugging tools, which is obvious, I think.
Okay, good morning, everybody. Yeah, my name is Volker Krause. I work for QAbstractItemModel. We have a booth downstairs, so if you want to learn about what we do. Yeah, domain-specific debugging tools. What is that about? Right, we have GDB and we have printf, so that should be enough, right? How hard can it be? Yeah, until we get a backtrace like that. And of course, we look at that and we immediately know where our problem in our QML code is. Well, that's maybe true if you're Thomas McGuire, who's doing the talk right afterwards on how the internals work. But for me as a normal developer, this is like complete nonsense, right? There's implementation details of QML. I'm lost in there with GDB. So obviously, just using the regular debugger is not enough. And there's several reasons for that. We have like increasing abstraction layers. Right, we get more and more away from the instruction level that we see with a regular debugger. We get asynchronous APIs, so there is no sequential control flow anymore. That also makes it much harder to just step through it with a debugger. Or even more so, we have distributed architecture, so multiple processes running on several machines. Again, I need to debug all of them at the same time. And then we have stuff like QML, which is interpreted at runtime. So if I look at that with GDB, I see the interpreter, but not what's actually happening. And to make it even more harder, we have just-in-time compilers. So the code I see with GDB is generated and yeah, tells me even less about where my actual problem is. So with the general tools we have, like the instruction level debuggers, the good old printf, and our profilers that measure CPU ticks or malloc calls, we are kind of on the wrong level there. So we are a bit lost in the complexity that we have in our applications today. So if you look at more detail where our problems actually are, take a few examples there. For example, the QtModel view framework. I guess some of you are using that. Very complex interface, lots of method calls that are happening on that interface. Quite hard to trace with a debugger. Another example is QStateMachine, right? The state machine you have in your mind is like the UML chart, but what you see in code is implementation details of the state machine. So the problem with a regular debugger is that we are looking at implementation details of a framework that is way below the semantics that, well, this abstraction is supposed to provide us. And if you put debug output in there with printf, if you ever tried that in a model that you wrote on your own, you get just way too much output because you can't target it on just the specific case where your problem occurs. The asynchronous APIs, most prominent example for that is network access. So if you use the QNetwork access manager, QNetwork replies, they emit signals once the network operation is done. Or more general, any kind of job-based API. So that if you want to follow what's happening there, like you could put another breakpoint in the result slot. But once you have more and more of those asynchronous objects, it becomes much, much harder to follow the actual control flow in your program, right? You have jobs running at the same time, so does that finish first, or does the other one finish, and what happens then? You easily get lost in the in the control flow. And with distributed architectures, that becomes even harder. Like an example for that is inter-process communication. Right? You have multiple processes that talk to each other. The interface is asynchronous as well, but what actually happens on the other side is even in a separate process. So you need two debugger instances at the same time, all kinds of breakpoints to follow what's happening there. So even more hard to see what's going on there. And additionally, if you have performance problems in that, right, you run a profiler on one program, you run a profiler on the other program, you see the costs there, but what you don't see is how much complexity do you have in the communication. So could you maybe merge 100 calls into one? This is only something you can observe indirectly. And of course, the runtime interpreted code, we have that in QML, we have that in WebKit. What you see there, if you look at backtraces like the example I had initially, is the code of the interpreter. And unless you wrote the interpreter, you most likely don't understand what's actually happening in there. So this is kind of useless, and it makes it very hard to correlate what you're seeing there to the actual bug in your QML or HTML5 code, especially for performance. Right? If you crash the interpreter, it's most likely a bug there, but you could work around it by changing your QML. But for performance, the bug is most likely not in the interpreter, but in your QML. And just-in-time compiled code, like we have it in JavaScript core and V8, which is used in QtScript and QtQuick, WebKit as well, makes that just even more harder, right? The debugger and the profiler see the generated code, and unless you can fluently read assembler and know how the just-in-time compiler works, there is no way you can correlate that back to the original JavaScript code. So, of course, you can use GDB and printf and all of that still on those problems, and they're still valid tools. But it is quite inefficient to work with them in complex frameworks. And it requires you that you understand how those frameworks work internally. And that's exactly what we don't want, right? This is why we build the levels of abstraction, so that you work on a much higher level without knowing how this actually works internally. Of course, it's still can't hurt to know how the stuff works, but requiring that for debugging JavaScript code, you know how the just-in-time compiler works is just nonsense. And it can lead to wrong conclusions, right? What you see very often in combination with QML is, oh no, JavaScript is horribly slow. Of course, if you look at the Colgrand output of your QML application, pure QML application, you might see a large part that is the JavaScript interpreter. But that doesn't mean that that is actually slow. It most likely means you just wrote slow JavaScript code. But since you lack the correlation, because the tools don't show you that, it leads to the wrong conclusions. So what can we do about that? And this is actually what this talk is about. So first of all, can we have better tools? And or how would better tools look like? And one thing we have to do is make sure the tool knows how the frameworks work internally, so that we don't have to. So move the knowledge into the tools. And show us the results on the same semantic level as the tool, right? We don't want to see what's happening inside the interpreter. We want to get meaningful results like this part of the QML code is slow, or this is where your bug is in the model view code. Of course, this has a big downside because it means that our debugging tools now become specific to one framework. So, which also means we need a lot more of them. Right? The nice part about GDB is it just works everywhere. So, where do we get those tools? For Qt, there is a large range of tools available. This is what Romain and I talked about on last Dev Days. The talk is still online, so there you get an overview on what's already available. But I guess most of you have built more or less complex stuff on top of Qt. So you have your own frameworks, your own components that do complex stuff. And very often there is no tooling available for that, because who would have written it? So we have to do it ourselves. And yeah, let's see a few indications that should, well, make you think about, is it worth building your own debugging tools? One is if you have very complex control flow in your application and you need 15 breakpoints to actually follow a specific case, and you keep doing the same over and over again there. If you have like the 50 points where you insert printf statements every time you have to debug a specific problem in one part of your application, or you have large debugging snippets already at hand that you just copy and paste in, that's another indication that there might be the need for some more structured tooling. Also, if you have very complex data structures or inside your component, and you keep drawing up graphs or something like that on paper over and over again, just to get an image in your mind what's actually happening in your application. So that's something where you might benefit from a dedicated visualization for this. And another example is if the performance metrics you get from your profiling tools don't really match what's actually happening in the application, right? So example would be you get the frame rate of your rendering system. But what exactly does that tell you? It only tells you your application is too slow. But how do you correlate that to this is where the problem actually comes from, right? If you render custom data, you want something that correlates that to a specific data file and the objects in there. So you can actually narrow down where the problem is. So those are all indications that you might want to invest a bit of time in writing your own debugging tools or profiling tools. And now we are going to look at a number of approaches to do this. Starting from very simple stuff, like built-in diagnostics, to external observation tools, to emulation tools, especially interesting if you're working on embedded systems or need access to specialized hardware or something like that, up to full integrated development environments. Overkill for most people, I guess, but there's actually a few people around here that have done this. And we look at API tracing and binary instrumentation as some of the more advanced tools to observe what your application is doing. And we'll see how you can use the QObject introspection mechanisms to build Qt-specific tools. Okay, so the first one, most basic one is typical printf debugging, right? The built-in debug output that works for built-in types. But if you have complex structures or complex types in your application that you use all over the place, of course you want to have support for printf output for those as well. And that is very easy to do with the QDebug stream operator, so you just overload that for your custom types. Like you probably have done that already. So this is like the most basic thing you can do. You just have to make sure that it's declared outside of the namespace, so it's actually found as a valid operator for QDebug, and then you can output anything in there that is helpful for you. any custom type you have that is used repeatedly, this usually is worth implementing. If you have your own libraries, there's two ways of implementing them. Inlining or as exported functions. Qt does inlining for all of them. I don't actually know why they picked this option, but it's one of those two that works if you just have it as a regular function. It's only available inside your library. So that's one of the concerns if you start building in debugging functions into your code is overhead. But this is actually, it slightly increases your code size because it's one extra function, but it has no runtime overhead if you don't use it. So this is like cheap enough. And if you really don't want to have it, there's a number of built-in defines to completely disable it. So this is nothing to be afraid of. You can add that for all your types. But this is just the most simple thing, right? Supporting your own types. What you usually want to do is either much more advanced diagnostics output for one subsystem, or build in some extra checks. Like the model view framework has lots of asserts built in that verify that your model is actually complying with all the API promises. And there's, in general, two ways of enabling them. You can do it at compile time with preprocessor defines, or you do it at runtime with environment variables. You can do it with config files, or we'll also see an example for IPC triggered output. This is useful if you have like a specific point in time where you need the output rather than continuously. Yeah, and you do additional checks or diagnostics. And this is built into your framework or component, right? And we'll see a few examples on how Qt does that. If you grep for _debug in the Qt code, you find hundreds of if-defs, usually one per class or one per smaller component, that allows you to enable additional, very detailed diagnostic output. There's just one example there for the QIODevice and the SSL socket. They are mainly useful while working on that component, but if you have very weird bugs working with that, it can also be useful to enable that, and you see what exactly Qt is doing as response to what you are trying to do. So having that available as for the user of a component is also useful in some cases. But it requires recompilation of Qt. So this is not very convenient. More convenient are the environment variables. And you'll find about 50 or 60 of them in the Qt code if you grep for getEnv, the system call for reading the environment variable. Just two examples there, Flash Paint, that visualizes all the widget paint operations. Very useful for paint performance and paint debugging. Debug just gives you full output of the debug communication, but there's many more in Qt. And this is, of course, something you can also do in your component. We'll see example. Right, for compile time conditional diagnostics, you just use if-defs. This is trivial. This code snippet is just a convenient example for doing compile time conditional debug output. So instead of if-defing each QDebug, you just define a macro that wraps the QDebug, and if you disable it, it has this kind of dead code here that the compiler optimizes away. So you can use your macro either in the stream way or in the printf style, and you have a single place where you can enable and disable it, and you don't have to wrap all of them into an individual if-def. So it's just slight convenience when doing this. you find that all over the place in Qt. And runtime conditional, also easy, right? You use the qgetEnv or getEnv system call for your environment variable. Typically, you put in an integer there to enable it, like 1 is on and 0 is off, because then you can easily convert that. But it's a string, you can put in whatever you want there. If you initialize it like this, right, it is a one-time thing, so there's no costly runtime overhead. And if you want to use that, it's one conditional check, and then if you have it enabled, the extra cost for the extra diagnostics. So again, very cheap and very convenient. But if you want to change the state of the environment variable, you have to restart the application to activate it. In many cases, that is okay. But if you have a bug that only occurs after several days, and then suddenly you need the diagnostics, right, this is a bit inconvenient. And that is where debug comes in. So if you're on Linux, debug is just readily available. On the other platforms, it works, but you need to do a bit more setup. But you might have some other IPC mechanism that you can use to trigger debug output, or any kind of other diagnostics. And this is just a little example where we have an extra slot that is marked as scriptable to do our diagnostics. And we expose that object to debuggers by registering the object, by registering a service, so we can actually address the application on the debuggers, and by registering the object that has our slot. And we can do that to every object where we need it. And then we can do a simple debug call from the outside and trigger this on demand. And it's always present in the application. So whenever the bug occurs without restart, I have my diagnostics available. Again, quick view on the runtime impact. So compile time diagnostics, obviously I can switch them completely off. So this is ideal for very expensive stuff, or stuff that opens security problems that I don't want to ship to customers. But it's not available all the time, right? So I need to do a special build to have my diagnostics. With environment variables, or IPC, I have it available all the time. And the overhead is really minimal, right? I have a bit of extra code size for the diagnostics code, and I have one read of an environment variable and some extra integer comparison or something like that. So this is nothing to be afraid of. This is really minor overhead. Usually you have much more or much bigger performance problems somewhere else in your code before you have to worry about the overhead of diagnostics like this. There's kind of a special case for built-in diagnostics, which I called compiled-in diagnostics. That would be like diagnostics code that is provided separately, not built into a component, that only uses public API to do some consistency checking or something like that. So you don't have access to internals there, have to work with the public API. A prominent example for that is model test. That is a one CPP file that you find on the internet, which you can link into your program, initialize it with one line, and it runs all kinds of consistency checks on the QAbstractItemModel. So the idea is very good. You have reusable consistency checks that you can just add to your application and run it, and it finds all kinds of problems in your implementation. The distribution, however, is not that nice. You have to find it on Google. Ideally, something like that would be shipped with the framework, right? So if you do that yourself for your own components, ship it to the user of that component so he can use that diagnostics easily. And then we get to slightly more complex tools. instead of compiling something into our application, we could build something that is just on the outside, observing what our application is doing. That, however, requires something that we can observe, right? This needs some kind of communication or some external effects. But very often we actually have something like this. A prominent example in Qt is the QDebus viewer. So this allows me to watch everything that happens on the debus IPC. That has no influence on the application, right? No change needed there. I just observe what communication happens. Not Qt specific, but in the same category is stuff like network sniffers that analyze all the TCP traffic, or database tools that show me what applications are doing on the database, right? So if I have something that has this kind of communication, maybe on some kind of special system, talking to hardware or whatever my application does, having a tool that visualizes what's actually going on there can be very, very useful in order to debug the application. Yeah, this is the debus viewer. It's actually showing the interface that I had in the previous example, where I can just activate the method there to dump the diagnostics output. So this goes nicely together with the debus triggered built-in diagnostics. Yeah, looking at the impact again, I don't need any changes in the application. Usually, there's also no one-time impact. It might make my machine slightly slower if I'm recording a large amount of data, but it's not influencing the application at all. It's available on demand, right? So I don't even have to restart, which is typically if I have a really hard bug that occurs at some point and it's hard to reproduce, so I need tools that work right away on demand. But it needs something that I can observe. And encrypted communication channels, for example, are, well, that's where we hit the limitations. We can't look into that. Oh yeah, this is an example on a small do-it-yourself project. Maybe someone has done that already. You know QDataStream, right, which is a kind of binary protocol to serialize Qt data types. Now, if you write that to a file and something goes wrong, it would be very useful to have an external tool that just visualizes you the structure of that QDataStream, right? That would be a perfect example for an external debugging tool. That would be even useful to all Qt developers, which just observes external actions of my application. Okay, then we have another category to look at, and that's emulators. So emulators are something that simulate the environment my application is running in. Most often that means simulate hardware or anything that is hard to reproduce or not available or very expensive, but which allows me to develop for that system. And it makes me independent of, for once, the hardware, if I want to simulate that, but also physical constraints. So very useful to simulate corner cases that shouldn't happen. An example in Qt is the virtual frame buffer. This, however, is just emulating the frame buffer hardware. So I can run my embedded program on the desktop and it shows me the output there. But that's about it. So this is the screenshot of it. I can even simulate some of the keys. But you see the limits there already, right? Emulating a touch screen or the user interface, this is, if I have to click this with the mouse, it doesn't really help me with getting a feel for the user interaction. It's just to see if the hardware access works. But there's more that I could do. And we don't have an example for that in Qt. Right, I can, for example, replay recorded input. So if I'm interfacing with some, let's say a car, I do the car HMI system, and I could record like the speed data and everything I get from the car, and then replay it to my application. And if it crashes after 3 hours, I replay the entire thing and I can narrow it down to where it actually happens without having to drive exactly the same path again. So for stuff that's hardly reproducible, this is quite useful. And it allows me to test corner cases that are otherwise very hard or expensive to do. Like if I have something that uses a GPS sensor, I developed the application here, so I know it works with positive coordinates because I'm in Western Europe. But what happens if I move to, say, Brazil, Southern Hemisphere? I suddenly have a different sign for the numbers. I actually had such a project, and our boss didn't want to send us to Brazil to test the GPS sensors. So if you can simulate that in software, of course, that is much, much easier and cheaper. And you can also test boundary conditions or invalid input you get from the hardware. That actually, it should never happen, but maybe you get coordinates that are just wrong. And you see how your application can handle that. And it's very useful in CI systems, right? Usually you don't have a car or a GPS sensor attached to your CI server and fly your CI server around the world to see if it survives crossing the date barrier. So you can emulate all those environment scenarios in software and run your unit tests with it. So how do we build something like that? First is find the right interface. So this is the part where you replace the actual implementation with the emulation. And there's some ways of doing this. If your hardware access, for example, is in a separate library, you could write something that is API compatible and you just swap out the DLLs. Slightly less work is if you're using something that already has some kind of backend abstraction. Qt Sensors, for example, that already has plugins for various backends. And then you could just write a fake backend, which you can feed with data, and still use the same interface, and your application won't notice the difference. Of course, you can also build that in your own hardware layer, right? You have backend abstraction and have various plugins to talk to different machines or a fake backend. Another good place is IPC or network protocols. Then you basically just write a fake server that provides the same interface or same protocol, and you feed in data from there. Once you have the interface, you can provide the data. And there's usually 3 ways you want to have. One is manually from the UI. This is, as you as a developer, you change all the knobs and all the values that the hardware provides you, and you see how your application reacts. So you can run your application in a debugger, and then you move across the date barrier in your fake GPS, and you see how it handles this. You also want to be able to do that from code, which is for unit tests, right? There you don't want to have the UI for controlling it, but the unit test should provide the different values, and you can test what's happening. And the third option is previously recorded files. This is the scenario after 3 days at a customer doing something, it crashes, and you need to have the full trace of what actually happened, and I want to be able to replay that. The recording, for example, can be done with all the previously shown methods. Like this is typically something you would build in and enable externally to write it to a file. maybe with an environment variable that specifies where to write it, and then you replay that with your emulation. Okay, and then we get the biggest solution, full development environment. This is mainly useful if you have like your own domain-specific language. And yeah, Qt Creator for QML is one such example in Qt. But in most cases, this is overkill. However, it's good to keep in mind that most of the IDEs, especially all the Qt ones, that's obviously the one we could easiest work with, are extendable by plugins. So instead of writing your full development environment, you might just want to add a few plugins to Qt Creator to support specific data formats you have. To have that all integrated or support a specific debugging tool you have. Especially interesting if you have, if you provide a software development kit that you ship to customers, right? For them, it's really valuable to have that all integrated. And this is not just theory. In the talk running in parallel from Sven Bergner, these guys actually have a full development environment for their domain-specific language. It's not built on Creator, but it's the same idea. So if you have something like that, it's really something to consider. Yeah, we all know Creator. Okay, and then I'm running low on time. I'll show you three more, or two more, I have to skip one, ways of building slightly more advanced tools. One is API tracing. And API tracing means you trace all calls to methods of a specific API, including their arguments. But that will usually give you a massive amount of data. So you need good visualizations and filtering tools for that. Yeah, and the way you do that is you intercept the API call. Easy, right? We'll see in a second how to actually do this. You record everything that comes in, and you do the actual method call. And yeah, some examples you might know. First one is strace, right? That traces all the system calls. So very useful to observe I/O behavior. So is it actually reading the correct file? Or where else is it searching? How many stats do I have in the file system? Also interesting for performance. And something that's becoming much more important for Qt 5, where we are using a whole lot of OpenGL, is a tool called API Trace, available for free on GitHub. That traces all OpenGL calls. And it has a nice Qt UI to visualize what you actually did with OpenGL. This is the screenshot. So here you have the full list of whatever. I think this is the chip demo from Graphics View running with an OpenGL backend. It shows you all the OpenGL state. It can barely see that here. You get nice thumbnails for every frame on what it actually looked like. So very useful to yeah, debug in detail OpenGL, look at it later on, go through step by step, analyze if there's too many operations that you might not need, so you can also look into that for performance. Now, how is this actually implemented? And there's three options for that. On some platforms, we have actually built-in tools for doing something like this. dtrace is probably the most popular. That's available on Mac and QNX. And on Linux, we have system-tab, perf, and uprobes. So with Linux 3.5, we also finally have the option there to do user space API tracing with the uprobes framework. And they basically allow you to define tiny breakpoints, so very low overhead. Inside user space functions, you get a callback that is triggered, and you can analyze the arguments or record them. Then there's POSIX ptrace. This is like a system call, very, very ugly and complicated to use, but that is what GDB and strace are using. Just for completeness, I wouldn't really, well, I didn't actually understand how to use it, so yeah, it's a bit weird. And maybe the easiest one, well, easy, LD preloading and overwriting of symbols. This is, for example, what the API trace tool is doing. So you can use the LD preload macro to load the DLL before everything else. And the symbols in there, if they happen to have the same name as the thing you want to trace, will overwrite them. And your methods will be called instead. So then you have the arguments, right? And you can record data on all that you want. And then you have to call the original function. And that's where it gets slightly tricky. Because you have to find the original function. It has the same name. If you just would call it, you would end up in yourself and have an infinite recursion. So you need to manually look up the symbol in the other libraries. So this is very ugly, with the DL-sim core does that. On Windows, it's way worse. I think you have to do some assembler magic. But in theory, it's doable, and there's examples out there on how this works. The nice thing is, this is a very universal solution once you have it working. It works without having, I think I have slides about that. It works without having the source code available, right? The OpenGL stuff, you usually have proprietary drivers where you can't look into, but the API trace tool doesn't care. It just hooks in before that and records everything and then calls the proprietary driver. Yeah, here again, let's look at the overhead. It's, despite all the ugliness you need to get this working, it's more or less just an extra function call. So for something that has like a high call frequency like OpenGL, this is not something you can completely neglect, but it's not that much. So for debugging, profiling, this is still perfectly fine. And it's only there if you use the tool, right? But it produces a large amount of data. So you need a way to quickly record that and afterwards to process it. And as I said, it doesn't require any modifications. It also works on stuff where you don't have the source code for. Okay, then I think I have to skip binary instrumentation. This is what Valgrind does. Even more crazy than the API overwriting. If you want to know more, Milian Wolf over there, he is the expert on that. He wrote this cool thing, for example. And that leaves me with one final approach, one that is slightly more manageable for Qt developers because it uses nice high-level Qt API, and that is Qt introspection. You all know that QObject has this meta object attached to it, which is why we need the mock precompiler. And that allows us at runtime to look into a QObject. And it tells us about signals, slots, properties, enums, the class name, the parent type, and so on. So this is quite useful already. And additionally, we get some global hooks in a Qt application. Some that are triggered for object creation and destruction, and one that is triggered for the application start. So what can we do with that? Oh yeah, examples. You might know Squish, the UI testing tool presented downstairs from FogLogic that uses this, and Gamma Ray, which I'll get back to in a minute. So what can we do with this? There's Qt startup hook, a method called from QApplication constructor. Unfortunately, I need to override that with similar methods as we saw in the API tracing. But this one is easier because it doesn't do anything, so I don't have to call the original implementation. So just a simple LD preload is enough to override that. And then I have like an entry point into every Qt application. So I can run my diagnostics code very early in the startup process, or just, well, inject myself there and wait for something interesting to happen. Like pull up a global event filter, or wait for specific objects to be created. Yeah, we saw that. Right, and then we have the add and remove hooks. Similar thing as with the startup hook. You need to override them with an LD preload trick or something like this. And then they get triggered from the QObject constructor and destructor. This would be nice because it allows us to just monitor what objects are created and destroyed, and then we watch out for the types we are interested in, right? And then we do whatever we want. However, they are called from the QObject constructor and the QObject destructor, which means too early or too late, respectively, for the virtual table to be complete. So if I ask for the exact object type, it will always be QObject. It hasn't run the constructors of the subclasses yet. And the other problem with this is this is called from whatever thread the object is created in, right? So I get calls there from all kinds of different threads. So I have to kind of protect against that if I want to record data in a central place. So very powerful tool, but slightly dangerous to use. Again, if you want to know the details of what happens if that is not thread safe and how to make it thread safe, Milian Wolf. So we want that power, but we want something slightly easier to use it. And that's where Gamma Ray comes in. That's kind of a framework for building debugging visualization tools for stuff based on QObject. It's free software, so you find it on GitHub. And it handles all the, how do I get into the application, how do I override that safely on all platforms. If you want to see a demo, I don't have time for that right now, but we have it at our booth downstairs. And it hides all the nasty details, and it provides you with a framework to build your own tools. So here's just some screenshots showing a state machine visualizer and some fancy object dependency graph. But yeah, what you actually can do with it is it allows you to write plugins, and it hides all the hook details we talked about. So what you get in the end is an object model, tree or flat list, or signals for objects being created or destroyed. And all of this is thread safe, so you don't have to worry about that. And it also delays the call long enough that the virtual table is complete, so you don't have to worry about that either. If you look at an object, it's fully constructed, and you can actually ask for the type and filter for your own types, for example. Okay, so what's the thing I actually wanted to show you here? With the increasing complexity in the frameworks we work with and the frameworks we build on top of that, and it's getting more and more and more, right? Tooling needs to keep up. And since it becomes more and more specific for the frameworks, we have to do some work ourselves. And that is nothing to worry about. It easily pays off, right? If you think about the amount of time you spend debugging something complex with a GDB or an instruction level debugger and printfs, if you would have spent that time on writing something that actually solves the problem for you, next time you run into the same problem, you have the tool available. And don't be scared about the overhead of compiling this into your application. Right? As we've seen, all the approaches that I showed you have minimal to no overhead at all. So, well, at worst, the code gets slightly larger. But I mean, this is a small price to pay for making it much easier to work with your frameworks. So next time you have this adding debug output again and again that you have done a few times already, think about if you can use one of the approaches I showed you here to put that in something in a way that is much more reusable and that you can share with your coworkers. Okay, thanks. That's all I wanted to show you. So, are there any questions?
One problem I have quite often is I'm being called from the event loop, maybe an asynchronous signal slot connection.
Mm-hmm.
I get some crappy parameters or why I called at all at this time. How do I find out who my caller is?
So this is about like a queued connection, right? If you have a direct connection, there's sender, and that is the queue object that sends the signal. So this is built in. For for a queued connection, it's actually harder, and there's no tool yet. We had some discussions on how to implement this. How queued connections are implemented by posting events into the event loop. So what you need is basically a hook into the creation of the meta call event, store the backtrace there, together in some sort of mapping with the event, and once you get called, this shows up in a global event filter and you can display the backtrace. So there is this theory on how this could be implemented, but so far nobody tried yet. So I can't give you a tool already that solves that problem for queued connections. But at least there are some ideas on how to do it. Sorry.
Are there any other further questions? Okay.
What would be the approach to handle model views? So you have
model view?
Yes.
Gamma Ray has a model view plugin. What that basically does is it shows you the complete proxy model hierarchy. So one problem in model view is like stacked proxy models, right? And you have a wrong result, and you never know which proxy models actually caused the issue. So one repeated code that we saw in projects where people added Q3 views on all the intermediate proxies and had like 15 windows, and you always mix them up. So we now have a nice hierarchical view in Gamma Ray where you can select the intermediate step. You see the state of that proxy model. You can look at all the details of that cell, what's in the model index, and what's in all the roles. What we don't have yet is recording for the various change signals, right, and checking of that. There is code in Gamma Ray. It's currently disabled because it was too slow for runtime attachable model tests. So if you know the model test.cpp, if not, Google for that.
Yes.
That's the only way to find it. You definitely want to try that on your model. What we try to build in Gamma Ray is make that runtime attachable. So whenever you have the problem, try it. But this is not done yet.
Okay. Thank you.
Okay. And if you have performance issues, the approach there would be to, most likely this is caused by too many signals or too broad change signals. So what one could do is record that and visualize what signals are emitted and how they propagate to a proxy chain. Right? Right often you have like one change, like one row added, and then the next proxy does a layout changed, and the next one does a reset, and then you propagate one tiny change to a massive change at the end of a proxy chain. And for that, having visualizations available would be very nice as well. Okay?
Could you tell us about the state of V8 JavaScript debugging with Qt? Other tools?
That would be something for Creator, right? Okay, apparently there's a presentation after lunch break about this specifically. QML tooling in general. So I haven't tried it with Qt5 yet. In Qt4 there's a JavaScript debugger for QML inside Creator. I guess and I hope that that still works with Qt5. But we'll see that after the lunch break apparently.
Are there any other questions? We have still some minutes. Okay.
What approaches do you use to debug performance problems?
Well, performance problem is a very general thing, right? The standard tools is something like call grins, so instruction level profiling. But as we discussed with model view, that might be like a way too low view. If you see the problem is in model view, you might want to look at what exactly is going on in your model. And a typical problem there is like explosion of change signals into something much broader. For painting, Gamma Ray, for example, has a paint analyzer that shows you all QPainter operations one by one. So if you have something that is paint related, right, you see in core grind, painting is the problem, then you look at what exactly is painted there. For OpenGL, there's the API trace tool. So if you have a problem in OpenGL, you look at exactly what's going on there. And usually you see something that is either done way too often, or you do operations that are way too expensive. And then you see how you can approach that. But if you just have it's too slow, start with something generic like core grind. Try to at least find the area, and then use specialized tooling in that area instead of making the wrong conclusion of, oh, JavaScript is too slow, let's rewrite it in C++. And that only looks faster because then your tooling shows you where the problem is. So, okay.
Is it okay? Last question, please.
One more.
What approach would you use to find heap corruption errors?
Heap corruption, well, the standard tool for that is Valgrind, which traces basically all memory operations and does consistency checks on them. That's available for free on Linux, on macOS as well, right? And there's well, mainly x86 and some ARM platforms, but I think there's an experimental but not yet working Windows port. And that basically uses the binary instrumentation to trace all memory operations, and then it remembers that, it shows you memory leaks, access to not allocated memory, double deletions, and all the standard memory problems. And from the same set, there's the massive tool, which is the heap profiler. So once you have fixed the corruption, you might want to minimize usage, and then this shows you a nice overview on where your memory allocations actually come from. Okay.
Okay, thank you very much for
Thank
this
you.
presentation.